Okay, I think we can start. Today we will continue with chapter 27. The topic is magnetic force on a current carrying conductor. We have a conductor and we drive a current on that conductor. So if you apply magnetic field on that current carrying conductor, then you will get magnetic force. So during the last lecture, we have discussed magnetic force on a charged particle, moving charged particle. So today we will talk about magnetic force on a current carrying conductor. So this is the working mechanism of the electric motors. So due to that effect, we are able to produce such electric motors. Here you see, today I will talk about the working principle of such electric motors. Here we have a conducting wire. The length of the wire is given by L, and the area of the cross-section of that conductor here, which is given by A, area of the cross-section. And we have positive charges within the conductor, and we apply magnetic field into the screen or into the paper. Okay, this is the direction of the magnetic field. So this is the direction of the current density shown here. So since we have positive charges, since we have current density in that direction, we can show that the drift velocity is also along the current density, okay? So positive charges are traveling with some certain drift velocity. So here we have charge, here we have drift velocity, here we have magnetic field, then there will be a magnetic force acting on that positive charge, okay? So by applying right-hand rule, we can find that the direction of the magnetic force acting on that charge is given by that expression, Q times drift velocity times magnitude of the magnetic field. But here, within that conducting wire, I have just considered the force acting on a single charge. But in reality, there are many charges here, okay? Let's consider that we have n charges in unit volume. This is the number of charges per unit volume, okay? And then the total force acting on each charge here. There we have many charges here, and we would like to calculate total charge on all of them. So the total charge is given by number of charges per unit volume times volume of the material. Within that volume, we have this number of charges per unit volume and the volume of the material, then the force acting on each charge we have calculated here, okay? So you can rearrange that one like this. What do you see here? We have N times Q times VD, drift velocity. This is given by current density. We have calculated this one during the last lectures, okay? And we also know that current within that conductor is given by current density times area, okay? So just put that number, put that equation here instead of this term, then we will have J here, and J times area will give us the current. Here we have length of the wire, here we have magnetic field, then the force, the total force acting on the straight wire, conducting wire, can be written like this: current times length of the wire times the applied field. So this is the magnetic force acting on a current carrying conductor. But what about the direction of the magnetic field? We know that from the last lecture, only the component of B perpendicular to the wire and perpendicular to the drift velocities of the charges exerts a force. So let's consider that this is the conducting wire. This wire it is located like this, and then we apply magnetic field in that direction. So there is an angle in between, phi angle here. This is the direction of the current. This is the length of the wire, and magnetic field is applied along that direction. So since magnetic field is aligned like this, we have a magnetic field component along the wire, along the current, and we have a magnetic field component perpendicular to the wire, okay? So we know that only that component can contribute to the magnetic force, only perpendicular component. So the magnetic force from that component will be zero, since we have drift velocity along that direction. So if you have drift velocity and magnetic field in the same direction, since we have a vector product here, the force will be zero. So only perpendicular component of the magnetic field will contribute to the magnetic force. So then the force here can be written like this. We have that relation, current within the wire and length of the wire, then the perpendicular component of the magnetic field. Perpendicular component is given by B times sinus phi. So then force acting on that conducting wire is given with that expression. The force is also always perpendicular to both the conductor and the field. We have already discussed this one because this is vector product, okay? So this is the direction of the current, this is the direction of the magnetic field, and by applying right-hand rule from current from L to B, okay, then you will get this direction of the magnetic force. For moving positive charge here, okay? For negative one, it will be reversed. Do you have any question here? Then we can represent that magnetic force acting on a straight wire segment with that vector product. The force is given by current times vector length of segment, length of that wire, and points in current direction, don't forget, okay? And times B, magnetic field direction. But here we have some different situation. What happens if we reverse the B, okay? So here, the B is along the X direction, and now I'm changing the direction of the B to the negative X. So if you apply right-hand rule from L to B, okay, like this, then this thumb will show the Neve magnetic force direction like this. So just keep the magnetic field here in negative X direction, but just reverse the direction of the current, okay? So we have just reversed the current. So here current was flowing like this, now current is flowing like this. Then in that condition, these fingers will show the current direction, then curl them to the B here, and then the thumb will show again magnetic force. So this is the situation for different cases. But what we have if the conductor is a curved wire? So what is the force acting on that curved conductor? In that case, we can divide it into infinitesimal segments, dl here, okay? And the force on each segment can be calculated like this. Here, what you see, here we have a wire, okay? Actually, there is another part here into the page and 3 segments, okay? So what do you see here? We have a straight wire here, okay? But here we don't have a straight wire. This is a curved conductor. And then you select a DL part here. And for each DL, we have different DF, okay? And this DF has X component and Y component then I will go into detail. We have an example for that case. So you have to integrate over that a curved conductor, okay, in order to find the total force acting on the wire. So here we have very nice example of that magnetic force acting on current carrying wires. So what is the working principle of loudspeaker? Here we have magnets, permanent magnets. Here we have a basket, and here we have a voice coil. Coil is a solenoid, okay? You send current, and then there's a wire here with many coils, which is called as solenoid, okay? So current is entering and goes out. Here we have a flexible suspension ring, and here we have rigid speaker cone. So these are the parts, components. And when you make them a pocket here, this is the magnified picture of the permanent magnet, this green one, and we have magnetic field lines from center to the magnet, okay, radial magnetic field. And what you see here, this color, let's say orange color, we have wires, okay, we have wires, and if you drive current, there will be magnetic. If you drive current, there will be a magnetic force produced by that permanent magnet on that coil, okay? So due to that force, this rigid speaker cone will be moved in that direction or in that direction, okay? So depending on the magnitude of the current, then you will have large movements in either directions. So if the direction of the current changes, okay, so let's consider that at the beginning the direction of the current is like this, then it goes to the right side, and if you reverse the current, then it will move into the left side. Okay, this is the working principle of the loudspeakers. Do you have any question here? Then let's continue with the example, magnetic force on a straight conductor. A straight horizontal copper rod here we have carries a current 50 amp from west to east. This is the current direction from west to east. In a region between the poles, a large electromagnet, and here we have an electromagnet, okay? Here we have electromagnet, and we can apply magnetic field in that direction. So this is the direction of the magnetic field, and the magnitude of the magnetic field is 1.2 Tesla. So in this region here, a horizontal magnetic field toward the northeast, okay? That is 45 degrees north of east with magnitude 1.2 Tesla. We have already seen it. Find the magnitude and direction of the force on a 1 meter section of the rod. So this is the length of the rod. Just choose 1 meter on that conducting rod, okay? So then calculate the magnetic force due to that magnetic field. While keeping the rod horizontal, how should it be oriented to maximize the magnitude of the force? So here we will have certain force due to the magnetic field. So the question is that how you can increase the magnitude of the force. So what you have to do, we will discuss this. So the force is given by that expression, I times current here, length, which is given, and times B, which is given, sinus phi. Phi is also given. Then here we have force 42.4 Newton. Okay. So what about the direction of the force? You have to align your hands, these fingers, along the current, and then curl them to the field. Then the direction of the force will be perpendicular to that plane and will be from screen to us, okay? So now second question. What was second question? While keeping the rod horizontal, okay, how should it be oriented to maximize the magnitude of the force? What is the force magnitude in this case? We would like to increase the force. If you would like to increase the force, you have to manipulate the phi because current L, B are constant, okay? So you can manipulate the phi, so you can rotate that wire in that direction like this, okay? Then for the sinus 90 degrees, you can get the maximum force. So if you make that rod perpendicular to the field, then we will get the maximum force acting on that wire. Then put all numbers here, then we have 60 Newton if this rod is perpendicular to the B. Okay, here we have another example, magnetic force acting on a curved wire. Here, first of all, just try to understand the wire. I will try to draw. The wire is actually like this. We have another part here. Maybe you cannot see, but we have another part here. Okay, we have 3 segments in the curved wire. So in this figure, the magnetic field is uniform and perpendicular to the plane of figure. This is the direction of the magnetic field. B is out from screen to us. Okay, this is the direction of the field. And the conductor carrying current to the left, this is the direction of the current. You can see, okay, direction of the current. And the conductor has 3 segments, 3 parts, 1 part, 2nd part, 3rd part. A straight segment with length L perpendicular to the plane of the figure. This is the first segment, which is perpendicular to the plane of the figure, okay? And semicircle with radius R, this second segment here, second segment with radius R, and another straight segment with length L parallel to the x-axis. This is the last segment here. 1, 2, 3 segments. Find the total magnetic force on this conductor. So this is the direction of the magnetic field. And we have F1 and F3 from the straight segments here, from that one and that one, we can calculate it. So in case of segment 2 in that part, we have to do something else, okay, which we have already seen. We have to solve an integral. So then we will combine all forces, magnetic force here, F1, magnetic force here, F2, and magnetic force here, F3. Then we will find the total magnetic force acting on the conductor. For segment 1 here, first part, L, the length is given by minus LK, and this is the direction of the field, and direction of the current, and they are in the same direction, okay? So then from the vector product, we will get 0 force from that component, from first segment, right? And for this segment, this direction of the current is along the negative x direction, okay? So then L can be written like this, minus Li, negative direction of the x. And then by applying that rule, Now magnetic field and L are, or current are perpendicular to each other, then we can get that expression I times L times B times J. So it is the resulting force is along the y direction by applying right-hand rule. So now let's try to calculate magnetic force for the curved segment. Just choose a very small length here, which is given by dl, okay? And let's consider that this is the angle theta from x-axis to the position of the dl, and this is the theta for very small segments, and this is the radius. We know from the physics 1, from the circular motion, that dl here, this small segment, is given by r times d theta, okay? Then what we have here, applying right-hand rule, this is the direction of the B out of the page, and this is the direction of the current here, dl we have here, and then the force will be like this. dF belongs to that infinitesimal part, okay? And this dF has two parts. One is along the x direction, the other one is along the y direction. And x direction can be written by cosine theta, df times cosine theta, and this part can be written df times sinus theta, okay? So just try to calculate these two parts. One is given by I times dlb here. What is dl? dl is given r times d theta. Put this dl here, then r times I times r times d theta, b times cosine theta for x component, and sinus theta for the y component. So to find the components of the total force, we integrate these expressions with respect to theta. What is theta here? Theta changes from 0 to pi, okay? From 0 to pi. Then these are the integral limits. This is the x component, I times r times b. These are the constant, then we can take them out of the integral. Here we have cosine theta, d theta. So what is the integral result of cosine theta, d theta? It will be sinus theta, okay? And sinus pi is 0. Sinus 0 is also 0. So the contribution from that one will be 0. You can also consider like this. dfx will be along that direction, okay? But here, if you go to that part, dfx will be in that direction, so they cancel each other. For this reason, this x component becomes a 0. So let's try to calculate y component. Here we have IRB, they are constant, put them to the left side, and integral limits for the theta from 0 to pi, and then sinus theta d theta. If you take this integral, you will get minus cosine theta. And here we have cosine pi, here we have cosine 0. Put them here in the solution of the integral. Then finally, we will get that expression, 2IRB. So what was the question? Total magnetic force acting on that curved wire. So then collect all forces. F1 is 0. F2 is given by that expression we have already calculated, and this is the F3. Then this is the final result. Do we have any question here? So now let's discuss the force and torque on a current loop. Here we have a current loop, okay? There is no resistor here, there is no EMF, okay? Just consider that we have removed them for simplicity, but this is a closed circuit and we have a current in the circuit, okay? Then I apply magnetic field B along that direction, okay? This is the direction of the magnetic field. So what are the force and torque on that current loop. We know that the force acting on each segment of the loop is given by that expression. F is given by current L times B. So here we have L given by B. This is the direction of the current. This is the direction of the magnetic field, and force will be like this by right-hand rule. Look at that part. This is the direction of the current from top to down, you can consider. And this is the direction of the B. Then magnetic field is like this. So they cancel each other, okay? Look at that part. This is the length. This is the direction of the current. And this is the direction of the magnetic field. This is the force by right-hand rule. Look at that segment. This is the length, which is given by A. This part is A, this part is B, I mean length of the wire. This is the direction of the B, and then this is the direction of the current. By applying right-hand rule, you can calculate that the direction of the force will be given like this. And this force also equal to that one. Then the net force act on the loop is 0, okay? The total force on the loop is 0. But torque is not 0. So just try to remember the torque. Torque is given by vector from origin to the force acting point. You can also remember like lever arm, okay, and force here. So let's consider that this is the rotation origin, okay. And since this force and this force are passing through that origin, that they will not contribute to the torque. But what about this one? The lever arm R to the origin will be given by B half times sinus phi, and here lever arm to the origin B half times sinus phi. Then you can get the torque like this. Okay, what is force here? Force is given by I times L times B. What is L? L is given by A here, and the lever arm is given by B half times sinus phi. So IBA is the force here and here, and B half times sinus phi. So B half here, we have normally B half. And since we have two contributions to the torque, here we have 2, then this 2 will cancel half here. Then the total torque acting on the system will be given by that expression. Like this. 2F B half sinus phi. Okay, here we have one F, another F, and lever arm given with that expression. F is given by IBA. A is length, okay, which is given here. So this 2 will cancel this 2, and then we have that expression for the torque. What do you see here? A and B. What is A? A is this length, and B is this length. What is AB? AB is the area of the loop, okay? The area of the loop is given by A times B. Then instead of A times B, put here A, capital A, area of the loop. Then the torque is given by I times BA sinus phi. This is the area of the loop. This is the current within the loop. Area of the loop, current in the loop. So that expression, current times area, is given by mu, which defines the magnetic dipole moment or magnetic moment of the loop. So mu is given by I times area. So instead of I times area, if you use mu, then the torque on a current loop is given by mu times B times sinus phi. This is mu, and this is B sinus phi. So a current loop or any other body that experiences a magnetic torque is also called a magnetic dipole. So here we have a current loop, okay, or anybody experiences a magnetic field like this, okay, so it is called as a magnetic dipole, and this is a magnetic dipole moment or magnetic moment. So then the torque here or torque here can be written in that form. Vector magnetic torque on a current loop is given by mu times B, vector product, of course. So then your four fingers are showing mu and then curl them to the B, and you will able to find the direction of the torque. So just have a look here. What about the direction of the mu? Direction of the mu is exactly on the direction of the surface normal. Here, this is the area, okay, this is the current, and this is the direction of the mu, which is perpendicular to the surface or plane of the loop. This is the direction of the mu, and this is the direction of the B. If you would like to calculate or if you would like to determine the direction of the torque, then just apply this rule from mu to B. By applying right-hand rule, you will see that the direction of the torque is this one. Okay, torque is along the y-axis. So here we have right-hand rule determines easily the direction of the magnetic moment. So we have given that the magnetic moment is given by I times area. If you know the direction of the area, just four fingers will show the direction of the current, okay? And the thumb will show the direction of the mu, okay? So what you see here, direction of the mu and direction of the surface normal, okay, are along the same direction. So mu is given by I times area. A is the direction of the loop's area vector. So in many problems, examples, direction of the current is given, then you can easily calculate the direction of the mu. And if the direction of the B is also known or given, then you can calculate direction of the torque. Okay, so this was magnetic moment of a current carrying loop. Here, what do you see? Here you will see a loop, a closed circuit, but we have just one loop, okay? If we have many loops like this, here we have current, and here we have many loops here. You see, one loop here, another loop, another loop, another loop, okay? Then it is called as a coil, in Turkish sarım, or a solenoid, okay, made from many loops. So you drive current in that direction, and then you have many turns. Here, N is showing the number of turns here, how many loops we have, okay? And each loop will contribute that magnetic moment, I, current in the loop, and area of the loop. So I times area, but here we have N number of loops, okay? Then the magnetic moment is given by number of loops times area times current in each loop, and then area of each loop. Then if you apply that rule, mu times B, mu is given, put it there, B sinus phi. So if you apply magnetic field on that solenoid or coil, here we have a coil, and this is the direction of the mu, okay? This is the direction of the current, you see. These four fingers will show the direction of the current, and then the thumb will show the direction of the mu. This is the direction of the mu, and you apply magnetic field in that direction, okay? From left to the right, this is the B. And what is the effect of that torque on that magnetic moment? So this magnetic moment will be aligned along the magnetic field due to the torque acting on that coil or solenoid. So let me draw like this. I strongly suggest you to always keep that information in your mind. If you have a magnetic field and you have a magnetic moment like this, okay? And this is the angle in between. What is the effect of magnetic field? Due to that torque, this magnetic moment will be rotated along the magnetic field, and finally, they will be parallel to each other. Okay? The magnetic field would like to align the magnetic moment along the direction of the magnetic field. So the torque will align the magnetic moment parallel to the magnetic field. Any question here? Then let me continue with potential energy for a magnetic dipole. You remember potential energy for electric dipoles, minus P times E. Maybe you remember if you check the previous lectures within that semester, beginning of that semester, we have seen this. So potential energy for a magnetic dipole in a magnetic field is given by that expression, minus mu times B. This is a scalar product. This is magnetic field, this is magnetic dipole moment. Here we have a current, and due to that current in the loop, we have magnetic moment like this, and the potential energy is given by magnetic moment times B. Here we have negative sign. And you can also write this one like this with cosine phi, because it is scalar product, minus mu B cosine phi. So what do you see here? This is the phi angle between magnetic moment and magnetic field. Here we have phi angle, or I can draw like this. Maybe it is better. So let's consider that this is the direction of the magnetic field. This is the magnetic moment. And this is the phi angle in between. What do you see here? When the phi is 0, I mean, if they are parallel to each other, phi is 0, okay? Then the cosine phi will be maximum. Since here we have negative sign here, energy will be minimum. So minimum energy means that magnetic moment will stay along the B because energy minimum is there, okay? So if you put phi is 90 degrees like this, this is the mu, and then the angle is 90 degrees. So energy will be 0, okay? Potential energy will be 0, but the energy is not minimum. 0 energy is not minimum. If you consider that this is the potential energy scale, this is 0, this is positive, this is negative. So here you have 0 potential energy, but here you have negative potential energy. Which one is minimum? Of course, this one is minimum, okay? Don't forget this. We have discussed all these things in the previous chapters. Check your lecture notes. So, potential energy is given by a scalar product of mu and B, but the torque, just to remind you, is given by vector product of mu and B, okay? Don't forget this. These two equations are very helpful and useful to deal with the magnetic dipoles and magnetic fields. Here we have one example, magnetic torque on a circular coil. Here we have a coil. As we have discussed, coil is formed from many loops, okay? Here we have many loops. A circular coil of 0.05 meter in radius. This is the radius of the coil with 30 turns of wire. Here we have 30 loops, lies in a horizontal plane like this. It carries a counterclockwise current of 5 amp. This is the direction of the current. Current is traveling like this, 5 amp. The coil is in a uniform 1.2 Tesla magnetic field directed toward the right. So here we have a magnetic field, which is given by 1.2 Tesla, direction of the magnetic field. And find the magnitudes of the magnetic moment and the torque on the coil. Since the direction of the current is given by applying right-hand rule, direction of the current, then this is the direction of the moment, okay? So by applying right-hand rule, you can easily calculate the direction of the magnetic moment, and this is the direction of the magnetic field. The magnitude of the magnetic moment and the torque on the coil is asked. So mu total magnetic moment for the coils or solenoid is given by I times area times number of turns. Here we have 30 turns, put 30, current is known, area is, radius is given, then you can calculate area, put the area here, then the total magnetic moment is given by 1.18 ampere square meter. So the angle phi between the direction of B and the direction of the mu is 90 degrees, okay, because this is in horizontal plane and this is perpendicular to the plane. Due to the direction of the current, we can get that information. So torque is given by mu times B and the angle in between, okay, like this. So we have calculated mu, put it there. We know the B, which is given 1.2 Tesla. And what else? We have sinus phi. Phi is 90 degrees, the angle between B and mu, 90 degrees. Put it there. Then finally, we have torque 1.41 Newton meter. The torque tends to rotate the right side of the coil down and left side up, like this. So this side will up, this side will go down, and finally it will be like this. This is the direction of the B. And finally, the direction of the coil will be like this. This is the direction of the mu, okay? Due to that torque, they will be parallel to each other. Do you have any question here? Then let me continue with another example. This is potential energy for a coil in a magnetic field. Here we have calculated the torque, and now we will calculate the potential energy. If the coil in the previous example here rotates from its initial orientation to one in which its magnetic moment is parallel to B, what is the change in potential energy? So it is asking that situation. So at the beginning, magnetic field is like this, and the coil is staying like this, and this is the direction of the mu. And after applying magnetic field, coil will be like this, magnetic moment of the coil, and this is the direction of the B. So the question is, what is the potential energy here? What is the potential energy here? Okay. So what is the change in potential energy? The change in potential energy, delta U, is given by U2 and minus U1. So potential energy is given by minus, here we know from that equation, minus mu B, or minus mu B cosine phi, scalar product. And here we have minus mu B cosine phi 2. Phi 2, what is phi now here? 0, okay? And minus potential energy in the first condition, which is given by minus mu B cosine phi 1. What is phi 1? 90 degrees. Put them here, then you will able to calculate the change in the potential energy, minus 1.41 joule. So the potential energy decreases because the rotation is in the direction of the magnetic torque. So what we have here, we have negative energy, negative change. So potential energy decreases, okay? So why it is negative? Because it is more minimum here, okay? Energy is more minimum here because due to the torque, this magnetic moment is aligned along the magnetic field as we have discussed. Any question here? Then let's continue with magnetic dipole in a non-uniform magnetic field. Here we have a magnet, permanent magnet. This is N pole, this is S pole, okay? And due to that permanent magnet, we know that we have magnetic field lines from N to S, right? From N to S, we have magnetic field lines. So we have just showed the magnetic field lines with blue color here on the right side, okay? And we put a loop here, which we have current I on that loop, okay? Due to the direction of the loop, we have magnetic moment of the loop. Magnetic moment of the loop is given by mu. We have defined by direction of the current. Mu is given by I times area, okay? Like this, direction of the current, and this is the mu. So, then here we have different small segments, infinitesimal segments on the loop. So due to the magnetic field, here we have magnetic field here, magnetic field here. What do you see here? That magnetic field is non-uniform, okay? So the magnitude of the magnetic field is decreasing. We are getting far from the pole to the right side, okay? And the direction of the B is also changes. So it is non-uniform magnetic field. So then due to the that magnetic field, there will be a net force to the right side, okay? These vertical components will be canceled. I will not go into detail. Then finally, we will have a net force to the right side. So then this loop will move to the right side. If the direction of the magnetic field is opposite, like this one, here I am using the same magnet, permanent magnet, but I have just reversed its direction. Here now I have N pole, and here I have S pole. Then field lines from N to S. From N to S, what you see, direction of the magnetic field is to the S pole, okay? Here from N pole, now here to the S pole, okay? Now we have reversed the direction of the magnetic field. Then the net force acting on the same loop will be reversed, okay? Then this loop will be moved to the S pole. So what do you see here? This is a magnetic dipole. And you can consider that each magnetic dipole has N pole and S pole. If you have a magnetic moment like this, due to that current in that loop, you can consider that this is N pole, this is S pole. This is N pole, this is S pole, okay? Poles of the magnetic moment due to that current in the loop. So since there is an attractive force between S and N, the force and the direction of the movement will be like this. Since there is a repulsive force between N and N, then we have force opposite direction. So you can consider like this. It is easier to understand the mechanism here. So the head of the arrow, let's say N pole, and the back side of the arrow is S pole for the magnetic moments. Don't forget this. It will be very helpful for you. So now let's go a little bit into detail, magnetic dipoles and magnets, how magnets work. Here we have an unmagnetized iron. Magnetic moments are oriented randomly. There is no net magnetic moment. Each magnetic moment cancel each other, okay? Net magnetic moment is zero. In magnetic materials, containing iron, cobalt, nickel, okay? So we have net magnetic moments of the atoms. So each atom in magnetic atoms has some certain magnetic moment, okay? But in unmagnetized magnetic materials, these magnetic moments are aligned randomly. So the net magnetic moment of the system is 0. But in a magnetized piece of magnet, just consider that this is magnetized, all magnetic moments here are aligned in certain direction, and then we have net magnetic moment. So this is the direction of the magnetic moment. This is N pole, this is S pole, okay? So what happens if I apply magnetic field in that direction to that magnet bar? So this is the direction of the magnetic moment. This is the direction of the B. This B will try to align that mu to the B, okay? There will be torque pointing toward the screen, okay, with that sign here. So this magnet will be rotated to the B, and then mu, magnetic moment or magnetic dipole, will be parallel to the B at the end, okay? This is the mechanism between magnetic dipoles and magnetic fields. Here we have another example. Here we have a permanent magnet, and there is an unmagnetized iron nail, okay? So it contains magnetic moments, but it is not magnetized at the beginning. It is like this. So how it could be attracted by the magnetic poles? It happens like this. The magnetic field of the bar, here we have magnetic field lines from N to S, okay? So here we have field lines. Due to that field lines on that iron nail, there is a net magnetic moment in the nail. So it becomes magnetized, net magnetic moment here. So then the direction of the magnetic moment will be along the direction of the B. So this is N, this is S, and S will be attracted. So this iron nail will be attracted by that permanent magnet. So if you reverse the magnet, again here you have an unmagnetized iron nail, and then here you have S pole. Magnetic field lines are like this, from N to S, okay? Then due to magnetic field produced by that permanent magnet, this will be magnetized. All magnetic moments, all magnetic atoms will be aligned along the magnetic field. Then I will have a magnetic moment along the magnetic field. Then this is N pole, this is S pole, then N will be attracted by S pole. So in both cases, this unmagnetized iron nail will be attracted by the permanent magnet. This is the mechanism between unmagnetized magnetic materials and permanent magnets. So, but this is important. This is unmagnetized iron nail, okay? So it contains magnetic atoms. So what happens if you use here copper nail or aluminum nail or brass nail or glass nail? It will not be attracted because copper, aluminum, glass, wood, glass, they do not contain any magnetic material, okay? But iron atom itself magnetic, okay? So cobalt atom itself magnetic, nickel atom itself magnetic. If this material, unmagnetized material, contains iron, cobalt, nickel, or mixture of them, then you can consider that this is magnetic material. So magnets can only attract the or repulse the magnetic materials. So this is another important information. Then let me continue with a bio application, magnetic resonance imaging, which is widely used in hospitals in order to get the picture of the body. Here you see a magnet, which is huge electromagnet. there is a solenoid or a coil here, okay? And you can drive very high currents because loop and solenoid made from superconducting material, okay? Then you can produce huge magnetic field here within the solenoid, okay? Then here there's a patient. You put that stage into the center of the solenoid. Then you can get the image of the patients. So what is the working mechanism? In magnetic resonance imaging, a patient is placed in a strong magnetic field here. Each hydrogen nucleus in the patient, so within our body, we have water and fat, and both water and fat contains many hydrogen atoms, okay? So each hydrogen nucleus in the patient acts like a miniature current loop with a magnetic dipole moment that tends to align with the applied field. Here we have magnetic field, B, okay, B. Then here, maybe you can consider like this. We have magnetic moment in the hydrogen atoms of the patient. And here we have magnetic B. B is produced by that device, and magnetic moments are present within our body, okay? So each hydrogen nucleus in the patient acts like a miniature current loop with a magnetic dipole moment that tends to align with the applied field produced by that guy. Radio waves of just the right frequency then flip these magnetic moments out of alignment. So you apply radio frequency to manipulate the magnetic moments. The extent to which the radio waves are absorbed in proportional to the amount of the hydrogen present. Then this makes it possible to image details in hydrogen-rich soft tissue that cannot be seen in X-ray images. So when you go to doctor, for example, in the hospital, there are more or less 3 possible imaging methods, okay? He or she can send you to the röntgen imaging or computed tomography or magnetic resonance imaging. So what are the main differences? So if you would like to get detailed images concerning bones, okay, X-rays are superior. They can give better resolution, better information in case of bones. But if you are talking about soft tissues, okay, then if you would like to separate differences between the soft tissues, magnetic resonance imaging gives much better resolution, much better pictures, much better information, we can say. Okay, now let's continue with direct current motor. We have discussed a little bit at the beginning of the lecture. Now I will continue. Here we have a basic schematic diagram of a simple DC motor. Here we have a magnet N pole, another magnet here with S pole, and you can consider that there will be magnetic field from N to S. This is the direction of the B due to the magnets from N to S, okay? And here we have a loop. This is the EMF source, and current goes in that direction. Okay, this is the direction of the current from positive to negative, from positive to negative. Here we have a rotor. Rotor is made from that one. This part and this part is the rotor, okay? This is a loop, conducting loop. And here we have a commutator. In Turkish, we can say çevirici, okay? I will explain the duty of that commutator, and due to that current, there will be a magnetic moment. You can get that magnetic moment by right-hand rule. This is the direction of the magnetic moment. Do you see? And here we have magnetic field between N and S poles. So then you can calculate the torque by right-hand rule. This is the direction of the torque. So along that rotation axis, this rotor will be rotated, okay? Then you can produce a DC motor. So like this. But what we have learned that this is the direction of the magnetic moment, this is the direction of the B. So due to that torque, this moment will be parallel at the end, okay? The magnetic moment will be parallel to the magnetic field at the end. Then it will be stopped. In order to prevent this, there is a commutator here. What do you see here? At the beginning, you start current from positive side of EMF, let's say, okay? From positive to negative, we have that current like this. But when the magnetic field and magnetic moment is along that direction are parallel, okay? What do you see here that maybe I should magnify the picture a little bit. What do you see here that there is no connection in between, you see? So current can pass through in that direction. But when the magnetic field and magnetic moment are in the same axis, so there is no contact between that blue part of the rotor and the circuit here, and there is no connection with the red part of the rotor and the circuit here. So there will be no current here because there is no contact, okay? In that condition, the current here is 0. So the rotor will be stopped, but I would like to continue to rotate the system. Whenever this is the direction of the rotation, whenever this part goes to the left side, it touches to the brushes here in the commutator, okay? Then current again pass through in that direction. So due to that design of the commutator, current always from positive to negative in that direction, and it is always rotating continuously. This is the working mechanism of direct current motors. So, but what about the power for electric motors? So the power of the system can be calculated by potential difference between this points and the current in the system, right? So this is the power input. And this VAB, what is this VAB in that circuit? VAB is given by EMF plus I times R. We are very familiar with this one. This wire has certain resistance and we have a current here. Then the voltage will be dropped due to the loss within the wire, okay? This is the internal resistance. But what we have here, which is quite new for us, we have another EMF. Here we have EMF source, which has VAB, okay? But due to the movement of the conductor, current carrying conductor, movement of the current carrying conductor in a magnetic field, another EMF is induced, okay? We will discuss that topic in chapter 29, okay? If you have a conductor and if you have a current in that conductor, if you change the position of that conductor in a magnetic field, then an EMF will be produced, okay? We will discuss this one later on. This is called as induced EMF or a back EMF, resulting from motion of conductors in a magnetic fields. So then this is the potential between that points. Here we have an example from the book, a series DC motor. A DC motor with its rotor and field coils connected in series has an internal resistance of 2 ohm. When running at full load, a 120 volt line, it draws 4 amp current. In Turkey, you can consider 220 volt, okay? What is the EMF in the rotor? induced EMF or back EMF, which we have just learned. What is the power delivered to the motor? What is the rate of dissipation of energy in the internal resistance of the rotor? What is the mechanical power developed? What is the motor's efficiency? What happens if the machine being driven by the motor jams so that the rotor suddenly stops turning? So this is the question. So first question, what is the EMF in the rotor? So we have learned that VAB, potential difference, is given by induced EMF plus dissipated voltage within the resistance of the system, I times R. So we know that VAB is given, okay, 120 volt here, then put it there, and the current is given. Where is the current? Current is 4 amp, resistance is also given, then put them here. Then the EMF is given by 112 volt. This is the EMF in the rotor, or back EMF, or induced EMF. So the power delivered to the motor from the source is given by power input VAB times I. Then this is the voltage, 120 volt, and this is the current in the circuit. Then we have input power 480 watt. What is the power dissipated in the resistance R? The power dissipated is given by I squared times R. We have done all the things in the previous chapters. I will not go into detail. Then this is the current. Take the square of the current, put the resistance here, and we have 32 watt. Okay, so this is the input power. This is the power dissipated, and the mechanical power output is the electrical power input minus the rate of dissipation of energy in motor's resistance, assuming that there are no other power losses in the system. So look at that one. This is the power output, which is asked within the question. The power input we have calculated 480 watt, and we have calculated power dissipated 32 watt. Then the power output is 448 watt. And another question is, what was the efficiency? Efficiency is the ratio of mechanical power output to electric power input. Power output is calculated here, 448 watt, and power input is also calculated here. This is the power input. This is the power output we have calculated here. Then we have 0.93. This is giving us the efficiency of the system, 93%. So now here we have another question. What happens if the machine being driven by the motor jams so that the rotor suddenly stops turning? So let's consider that motor is stopped. When the motor is stopped, the back EMF will be 0, because we have learned that the back EMF or induced EMF resulting from motion of conductors in a magnetic field. So if this conductor current carrying loop is moving in the magnetic field, then there will be EMF. If it is stopped, there will be no induced EMF, okay? Let's consider that the motor is stopped. The back EMF, which is proportional to rotor speed, since the motor is stopped, it will be 0. Then the current within the complete system will be like this. This is the potential difference already given. This is the internal resistance of the system. And the current in the system will be 60 amp, okay? If there is no back EMF, because it is stopped. Then the power dissipated will be completely different. Here we have 60 amp. At the beginning, it was 4 amp. Now motor is stopped and 60 amp is traveling in the circuit. With that 60 amp, we will get that power, 7,200 watt, 7.2 kilowatt. this is huge power and huge current passing through on that circuit. Then remember the fuses, okay? If this massive overload does not blow a fuse or trip a circuit breaker, the coils will quickly melt because the current loop or conductor will be very hot because there is a huge power dissipated in the circuit or huge current pass through within the system. When the motor is first turned on, there is a momentary surge of current until the motor picks up speed. So just consider that this is the rotor. At the beginning, it is at rest, okay? When you apply voltage, it will start to rotate like this. And at the beginning, it will be slow, okay? Since it is slow, the back EMF will be small, okay? Then the current will be very huge, as we have discussed here. When you start motors at the beginning, okay, they will get huge current since the back EMF is small. Then the voltage drops in the power lines supplying the current. And this voltage drop will be greater than the usual. Similar effects are responsible for the momentary dimming of lights in a house when an air conditioner or dishwasher motor starts. So in air conditioner, in the external unit of the air conditioner, there is a huge motor, and also in dishwasher or other, let's say drilling, for example, electric drilling, there are motors, and at the beginning, they drive huge currents, okay? Since there is no rotation or very slow rotation at the beginning, they will drive huge currents. Then there will be voltage drop in the whole system. Then the brightness of the lights will be less, okay? It also happens in homes, in a house, or also you can see in laboratories, in industry buildings, for example. Do you have any question here? So this is the last topic, the Hall effect. Here we have a strip made from conductor. Let's consider like this. Let's consider this is completely made from conductor. It has certain thickness and it has certain width, okay? And we drive current in that direction. This is the current density. And we apply magnetic field in that direction. So we have current density along the x-axis. We have magnetic field along the y-axis. And the charge carriers are electrons, negative charge carriers, okay? So what do you expect? Since we have negative charges, the drift velocity will be opposite to the current density, right? This is the direction of the drift velocity. This is the direction of the magnetic field. Apply the right-hand rule, then we will get the direction of the force acting on electrons. Okay, so then electrons will be deflected like this. They will be collected here. Then that part of the conductor will be negatively charged, and that part of the conductor will be positively charged, okay, due to that movement of the electrons. Electrons are collected here. So since this part is negatively charged, since part is positively charged under the magnetic field, there will be an electric field from positive to negative, from higher potential to lower potential, okay? So due to that electric field, there will be another force opposite to the electric field and opposite to the magnetic force in that direction. If you increase the magnetic field, so this force will increase and negative charges will be collected here. Then after collection of negative charges here, positive charges here, you will increase the electric field by time. And in some point, there will be a steady state in the system. This magnetic force and electric force will be equal to each other, and the system will be stable. Okay, so we will discuss this one. So this is called as, this potential difference between that end and that end of the conductor is called as Hall EMF or Hall voltage. Okay, at the beginning there is no voltage difference, just we have a current. This is the current density, and electrons have that type of drift velocity opposite to the current density, and just you apply magnetic field, and then electrons will be collected here, positive charges will be collected here, then there will be an electric field in the system. So we produce a Hall voltage, okay, here in between. So this is also called as Hall EMF or Hall effect, okay? So now let's consider positive charges. In case of positive charges, we have current density again here along the x-axis. And since the charges are positive, drift velocity is along the current density. Then if we apply magnetic field in that direction, there will be force acting on the positive charges in that direction. This is magnetic force, okay? Then positive charges will be collected here. Negative charges will be collected here. Then due to the potential difference between the two parts of the conductor, there will be an electric field and electric force in opposite direction to the magnetic force. Magnetic force, electric force. So electric force is due to the potential difference between the each side of the conductor. So this is called as Hall effect and valid for both positive and negative charges. Then let's try to get a relation between electric field and magnetic field, electric force and magnetic force. In the steady state, it means that magnetic force and electric force are equal to each other. Then the total force acting on that charge will be zero because they cancel each other. The electric force in that direction is given by Q times Ez along the Z direction, and the magnetic force is given by Q times drift velocity times magnetic field along the Y direction. They are equal to each other. Put that one to the right side and cancel the Q's on both sides. And Ez, electric field, is given by minus drift velocity times magnetic field. So here we have drift velocity. And from the previous lectures, we know that the current density is given by N times Q times drift velocity. Okay, this is number of charge carriers in unit volume. This is the charge of each charge carrier within the conductor. This is the drift velocity. Take this drift velocity and put it there. Finally, we will get that expression N times Q is equal to minus Jx times By over Ez. What do you see here? Current density is known, magnetic field is known, and electric field potential difference can be calculated, okay? Q is the charge of electron. In case of positive charges, again, they are same, okay? And we can calculate number of charge carriers in unit volume within the conductor, or concentration of mobile charge carriers. So this formula gives us concentration of mobile charge carriers within the conductor. And very useful formula. With that example, I will finish my lecture. Here we have a Hall effect measurement. We place a strip of copper, this is, okay, 2 millimeter thick. Thickness is this part, okay, this is the thickness, and this is the width. This is the thickness, this is the width, 2 millimeter thick, and width is 1.5 centimeter in a uniform 0.4 Tesla magnetic field. Magnetic field is in that direction. When you run a 75 amp current in the positive x-axis, okay, in the positive x direction, we derive 75 amp current. You find that the potential at the bottom of the slab is 0.81 microvolt higher than the top. So you apply magnetic field, you drive current, and then there will be a potential difference in between. And it says that the potential here is higher than that point. And what is the potential difference? 0.81 microvolt, okay? From this measurement, determine the concentration of mobile electrons in the copper. So how many electrons we have within that copper? So this is the formula. Number of the charge carriers, you can use that formula. Put Q here, okay? Minus Jx by over QEz. Q is known, charge of electron. E is known, which is given here. We can calculate. B is known. We can also calculate current density. Current density is given by current per area. Current is given. Area you can calculate because the cross-sectional area is given, okay? Width and thickness are given. Put them here. Then the current density is given ampere per square meter. And electric field is given by the potential difference between two sides of the copper and distance in between. Distance is given and the potential difference is given 0.81 times 10 to minus 6 volt, microvolt, volt. Okay, then electric field is given by volt per meter. Put this Jx here, put Ex here, then we can calculate number of charge carriers, number of electrons here within that copper. 11.6 times 10 to 28 electrons within unit volume, okay, within that copper wire. So this was the last transparency of that lecture, and with that lectures I have finished the chapter 27, and next week we will continue with magnetic field sources, inshallah. Do you have any question with that part of my lecture? Any question?
Can you repeat the previous page?
This one?
Yes.
Okay, of course. So here I have a conductor, okay, and there is no magnetic field, there is no current at the beginning. Then I drive a current along the x-axis. This is the current density, okay? Let's consider we have positive charges. In semiconductors, there are holes. They can be considered as positive charges. We have already discussed in the previous lectures. So there is a current within the conductor. Whenever I apply magnetic field, there will be a force acting on the charges. This force is given by Q times the drift velocity times B, QVB, right? This is the direction of the force. Then the positive charges will be collected here on top, and negative charges will be collected here. So this side will be positively charged, this side will be negatively charged, and there will be potential difference in between due to magnetic field. Okay, this potential difference is called as Hall EMF or Hall voltage, okay, due to the Hall effect. So at certain point, the magnitude of the magnetic force and magnitude of the electric force due to the electric field from higher potential to the lower potential, here we have an electric force, which is given by Q times E. The magnitude of magnetic force and magnitude of electric force are opposite to each other, and in the steady state, they will be equal to each other. So then the total force acting on that charge will be zero. So electric force, Q times E, plus magnetic force, QVB, will be equal to zero. There will be no net force acting on the system in the steady state when the magnetic force and electric force are equal to each other. So then the electric force can be written with that expression, minus VDB. Here we have VD, Instead of VD, we can use that expression. We know that the current density from the last lectures, we know that the current density is given by N times Q times VD. Take VD and put it here, J over NQ, okay? Then you can get that expression. Let me do, okay? So here we have EZ. Instead of VD, I will use JX over NQ, okay, times EY. Or if you take NQ from that expression, you will get this one, minus JX BY over EZ, okay? This one. This N here, number of charge carriers in unit volume. This is the charge of the charge carriers. This is the current density. This is the magnetic field we applied. This is the electric field between 2 points, okay? And here we have potential difference due to the Hall effect. This is called as Hall effect. Do you have any question? Is it clear now?
Yes.
Okay. Any other question? Evet. Kendinize iyi bakın. Sağlığınıza dikkat edin. Ailelerinize selamlarımı iletiverin. Görüşmek üzere.